Type 3 indeterminate forms include exponential functions, so there would be a distinct way to go about evaluating them. Learn the trick here in differential calculus. The last three types of indeterminate forms are 1 raised to infinity, 0 raised to 0, and infinity raised to 0. The exponents are taken as limits, so the laws of logarithms would come into action. Recall from basic algebra that in order to pull down a variable exponent, one should take the logarithm, and the rule then allows the exponent to go down as a coefficient. Here's the first example of type 3 indeterminate forms, with the limit of sine x raised to tangent x as x approaches 0. By plugging 0 for x, we get sine of 0 raised to tangent of 0, simplified as 0 raised to 0. Tangent x should turn into a coefficient, so we can work with a product or with type 2 procedure. So we first complete the function by injecting y, then take the natural logarithm of both sides of the equation, making ln of y is equal to ln of sine x raised to tangent x. And with the rule of logarithm, we can have tangent x times ln of sine of x. Not only did we make the exponent another term, but we also generated the product. We can then convert the expression into a quotient, and we transfer tangent of x into the denominator. That will make the expression ln of sine x upon 1 all over tangent x. From trigonometry, we know that the reciprocal of tangent is cotangent, so we can write the denominator as cotangent x. Now, we are ready to apply L'Hopital's rule. So take the derivative of ln of sine of x over the derivative of cotangent of x. With the format of u prime over u as the derivative of ln, the expression turns into the derivative of sine x upon sine x all over the derivative of cotangent x, which is negative cosecant squared of x. The derivative of sine x is cosine of x, making the numerator cosine x over sine x. Then convert cosecant squared of x into the reciprocal of sine squared of x. At this point, we can cancel some sine x, making the expression negative sine x times cosine x all over 1. With x as 0, we have negative sine of 0 times cosine of 0, making the whole equation simply ln of y equal to 0. However, we aren't looking for ln of y, but instead just simply y. We need to revert back our initial operation of injecting ln into the limit, and that is through the natural number e. We get e raised to ln y as equal to e raised to 0, which can then be simplified as 1. E and ln can cancel out, resulting to y as 1. So the limit of sine x raised to tangent of x as x approaches 0 is 1. Another type 3 indeterminate form example is the limit of the quantity 1 plus 1 over x squared raised to x as x approaches infinity. With x as infinity, the expression turns into 1 plus 1 over the square of infinity, and everything is raised to infinity. 1 over the square of infinity is 0, so the whole expression turns into 1 raised to infinity. Having proven that we indeed have a type 3 indeterminate form, we start the evaluation by completing the limit. Assume y is equal to the quantity of 1 plus 1 over x squared raised to x. By inserting ln on both sides, we get ln of y as x, ln of the quantity 1 plus 1 over x squared. Having a product, it is easy to convert it into a quotient. This time, we use x as the denominator, so the expression turns into ln of the quantity 1 plus 1 over x squared, and everything is over the reciprocal of x. Now that we generated a quotient, we apply L'Hopital's rule. So take the derivative of the numerator, ln of 1 plus 1 over x squared, and also the derivative of the denominator, 1 over x. With ln in the numerator, the derivative will turn as another ratio with u prime and u. The expression becomes the derivative of 1 plus 1 over x squared upon 1 plus 1 over x squared. And this ratio is divided by the derivative of x raised to negative 1. The derivative in the numerator can be distributed among 1 and 1 all over x squared. The denominator also becomes negative 1 times x raised to negative 2. Moving further, the derivative of a constant is 0, reducing the function into the derivative of x raised to negative 2 upon 1 plus 1 over x squared, and this is divided by negative 1 over x squared. Now, the derivative makes the numerator negative 2 times x raised to negative 3, and the denominators can be placed all together below as negative 1 over x squared multiplied by the quantity 1 plus 1 over x squared. To avoid getting confused, write the numerator as negative 2 over x cubed, and the x's at this point can easily be cancelled out, making the function negative 2 all over x times the quantity of 1 plus 1 over x squared. With infinity as x, the function becomes negative 2 over infinity times the quantity of 1 plus 1 over infinity squared. Simplify the fractional term to have negative 2 over infinity times 1 plus 0, making the whole function as negative 2 over infinity. So ln y is 0. Just like how we proceeded with the solution from the previous example, take e of both sides of the equation to get e raised to ln y as equal to e raised to 0, which is 1. By cancelling e and ln, we get y as 1. So the limit of 1 plus 1 over x squared raised to x as x approaches infinity is 1. Another limit of type 3 is the limit of the quantity 1 plus 1 over x raised to x squared as x approaches infinity. Check if the limit brings about indeterminate form by plugging x as infinity into the limit. So we got 1 plus 1 over infinity raised to infinity squared, which then turns into 1 plus 0 raised to infinity. And true indeed that the function is a type 3 indeterminate form. So take down the exponent by injecting ln into the function to have ln of y as x squared times ln of 1 plus 1 over x. With the exponent turning into another term, a product is created which can then be further transformed into a quotient. Let's take x squared as the denominator, making the function as ln of 1 plus 1 upon x all over 1 over x squared. To start with L'Hopital's rule, we take the derivative of ln of 1 plus 1 over x, and also the derivative of 1 over x squared, which turns into the derivative of 1 plus 1 over x upon 1 plus 1 over x for the numerator. Then again, the denominator can be transformed into the derivative of x raised to negative 2 to easily use the power rule. Distribute the derivative among the terms in the numerator to get the derivative of 1 plus the derivative of 1 over x. These are all over 1 plus 1 over x. And the denominator's derivative turned out as negative 2 times x raised to negative 3. The derivative of 1 is 0, and 1 over x can be written as x raised to negative 1. Then, the derivative of x raised to negative 1 is negative 1 times x raised to negative 2, which can then be written as negative 1 over x squared. All the denominators can also be grouped together in a single main denominator, with negative 2 over x cubed times the quantity of 1 plus 1 over x. Now we can cancel some x's, so the reduced expression is x over twice of the quantity 1 plus 1 over x. When we plug infinity for x, we get the expression infinity over 2 times 1 plus 1 over infinity. This can be reduced into infinity over twice of 1 plus 0, or that would be taken as infinity over 2. So ln of y is infinity. If ln of y is infinity, take the natural number e into both expressions to make e raised to ln y as e raised to infinity, which is simplified as infinity just the same. Cancel e raised to ln to get y as infinity. So the limit of 1 plus 1 over x raised to x squared as x approaches infinity is infinity.